All right, welcome to our lesson on medians, altitudes, and perpendicular bisectors, and we'll actually also talk about angle bisectors within triangles. All four of those things I just mentioned are segments that come from the vertex, or from the three vertices of triangles. Before we get started, I apologize. I have a dog with me here. I know some of you are allergic to that, and I hope that doesn't bother you as you go through this. If your eyes get puffy, though, you'll know why. All right. The median of a triangle is a segment that goes from a vertex to the midpoint of the opposite side. Each triangle will have three medians, okay? So if you have an acute triangle, let's see what that looks like first of all. Those would be where the vertices are, and now I'm going to mark the midpoints because the segment's going to go from the vertex to the midpoint of the opposite side. To know that we're talking about a midpoint, we need to mark that that marks it into, or creates two congruent pieces, two congruent segments within that side of that. So without a doubt, this is the midpoint of this segment, and this is the midpoint, and this is the midpoint. So that is a median. There's two more medians, like so. So it goes from the vertex to the opposite sides. Over here in the right triangle, there I'm just marked those vertices with the green dots. Those are the midpoints. See, I proved to you those are midpoints. And then we have three medians that go from the vertex to the midpoint of the opposite side. Notice that they all intersect. We'll do the same thing for the obtuse triangle. There's really no difference here. They meet there in the middle. Medians are always inside the triangle. All nine of the medians that we drew in those three triangles are inside. Okay, the intersection, and anytime you have an intersection of three or more lines, we call it a point of concurrency. So the point of concurrency of all three medians, or the intersection of all three medians, is called a centroid. What an awesome word there. So we have three centroids. This is the centroid, I've circled it here in yellow, of those three triangles. The centroid, this is pretty awesome, is the center of gravity of it. So, like, if you have a triangle and you can find the centroid, you could balance it at that point. All right, an altitude. If you think of altitude, you think of how high something is, and if you think of how high something is, it has to be perpendicular to it. So it's the perpendicular segment from a vertex to the line containing the opposite side. So it's similar to this, except they're not going to go to the midpoint. It's going to make a perpendicular piece. So if we're talking here, if we got this vertex up here, if we're going to talk altitude, I could draw a line, but I hope you see that that line is not perpendicular. Nor is this, nor is this. So where is it perpendicular? Right about in there. So we're going to draw a segment, and we'll say that it's perpendicular with the right angle there. That is an altitude. Now there's three more altitudes from each of the, or there's two other altitudes in this triangle rather, from this vertex. Now to draw these, turn your paper around so that this side here is horizontal, so that it's like on the bottom, if you will. So it makes it easier to draw a straight and a perpendicular piece. But you see how that makes a right angle? And we can do one more from over here. Notice that they intersect as well. Look what happens on the right triangle. We have these three vertices. From the right angle, it simply just drops to the other side and makes a right angle. That is the altitude, how high this point is from the other side. Look what happens on the other ones, though. If we're going to go perpendicular from this point to this side, well, that's the leg. Okay, and same thing over here. To go from this point to the opposite side, we're talking about the leg. The legs are the two altitudes of a right triangle, or two of the altitudes, I should say. Now let's talk about the obtuse triangle. If we talk about from the obtuse angle, it's pretty easy to drop an altitude over there and make a perpendicular line. But notice what happens if we're talking about perpendicular segments. Nothing inside the triangle is perpendicular. Do you see that? We're going to have to go outside the triangle to get to perpendicular to the side. So the first thing we need to do is actually extend the side. And do so with a dotted line here, because it's not actually a part, it's not a side of the triangle, it's the line that contains the side of the triangle. And so therefore, how high this is the perpendicular altitude is outside the triangle. Kind of like if we're talking about sea level, if I'm in Nashville, Tennessee, I am not above the sea. If I look down below me, there is no sea. But I'm above sea level because the sea level extends, if we go from Florida, if this is the sea, it would extend to underneath me here somewhere, and there I am here in Nashville. There's your example for that. And if I want to do the other one, I'd have to extend this line over here. Altitudes of acute triangles are always inside. These are the altitudes that are always inside. One altitude of a right triangle is inside, and then the other two are legs. That's what we're discussing. And if we're talking about an obtuse triangle, two altitudes are outside and the other is inside. We'll practice the ones from the obtuse one. They're a little bit tricky to draw. The point of concurrency, where these three intersect, is called the orthocenter. Isn't that kind of awesome? An orthocenter. Look, I have to extend these really far out here on this obtuse one. The orthocenter of the acute one's here. The orthocenter of a right triangle is the vertex of the right angle. The orthocenter of this one is way out here. They intersect down here. All right, so that gets us our definitions of an altitude and a median. We talked about what a centroid is. It's where the three medians intersect. This leads us to our centroid theorem. If the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the intersection of the opposite side. This sounds way more confusing than it is. That orthocenter we were talking about, which is this point C, it's 2/3 of the way across for the entire median. So this piece is 2/3 of the median, and this piece is the other third. If we're talking about this median here, DG is 2/3 of DJ, and then or DC that is, and then DC is 2/3 of DJ, and CJ is 1/3 of DJ. HC is 1/3, CF is 2/3 of HF. So over here in this example here, if GE is equal to 24, as a length of 24, then GC is 2/3 of that. Now, I'm going to do this with an equation. The math of this is really simpler than what I'm about to show, but the segment addition postulate allows us to say that GC plus CE is equal to GE, right? CE is double GC. This is 2/3, this is 1/3. So CE is equal to 2 times GE, or GC rather. I'm going to plug this into the equation using substitution, and I can solve this and say that 3 GCs is equal to 1 GE. So if GE is equal to 24, what is GC? What is this smallest piece over here? Well, it's 1/3 of 24. 24 divided by 3 is what this is. Okay? CE will be double that. CE is double the 2/3. Now, the math of this is pretty simple. These are in thirds, so if you can divide 24 by 3, this is one of those thirds, 8 is, and then this is going to be 2 of those thirds. 2 times 8 is 16. Okay? So if it's given to you this way, if DC is equal to 8, okay, that is 2/3 of the distance. That's the bigger piece of DJ. So CJ is going to be one of those thirds. So if 8 is 2/3, what is CJ? It's half of that, 4. And then what's the whole of it? 8 and 4 is 12. Okay? So 12 divided by 4 is, 12 divided by 3 rather is 4, and then double that is 8. That's how, so we can just work those things by dividing by 3 and multiplying by 2 is really what this is about. We'll practice this in class as well. I'll do this one with you. Number 1 here. All right. We have to figure out what X, Y, and Z are. I'm going to do X. I'll let y'all figure out what Y and Z. So here's the deal. This piece is 6X. This piece is 15. RU and UC. Which part's the smaller one? Well, RU is. RU is 1/3 of RC. UC is 2/3 of RC. So two of these, two RUs, will make two UCs. Two RUs will make one UC. So if I say 2 times 15 will equal 6x, that's how we will solve for x. Go ahead, use that model and see if you can solve for y and z. Pause the video. Did you say that 2 TUs would equal BU? I hope that you did. And that leads you to y equaling 5. That is what y equals. For z, this is what you should have ended up with. All right, the next piece of this puzzle, it's really putting two concepts together that we already know. A perpendicular bisector is a bisector that is perpendicular. A segment bisector is something that goes through the midpoint. So this is like the median. It's going to involve a midpoint, but it's going to be perpendicular to it. All right, so a perpendicular bisector is a segment of a segment is a line, array, or segment that is both perpendicular and it goes through the midpoint of the segment. All right? So in the diagram over here on the left, XY is a perpendicular bisector. B must be the midpoint because there's two congruent segments. So, oh, that's totally backwards. Hold on. There. XY is the perpendicular bisector. It is. They're both perpendicular to each other, but the one that is being bisected is AC. XY is a perpendicular bisector of AC, but not the other way around. If we're talking about triangles, when there's three perpendicular bisectors, the intersection of those is called the circumcenter. Check out this diagram over here. If I got my midpoints and I'm going to make perpendicular bisectors, there is the perpendicular bisector of this side. Here's the perpendicular bisector of this side. And this is the perpendicular bisector of this side. Notice what's different about these is that they don't go through the vertex, the vertices. These are not altitudes. Perpendicular bisectors and altitudes are not the same things in most cases. More to come on that. But this point right here is called the circumcenter. Let me pause what we're doing here for just a second. Take a break from your notes here. I just want to show you something. Angle bisectors of triangles matter too. They will intersect at another center. There's actually 4 centers. The centroid, the circumcenter, the orthocenter, and then this center as well. I want to show you something else that's pretty awesome. These are the altitudes of that obtuse triangle, right? That would be the orthocenter. Okay, I'm going to add under that the medians of that same obtuse. That would be the centroid. And now I'm also going to show you the circumcenter, where the perpendicular bisectors intersect. Check this out. They are all on the same line. They're collinear. That's called the Euler line. It's not going to show up on a test or a quiz, but isn't that fascinating that those three there's centers of a triangle? The fact that a triangle can have all these centers is strange too. But there's some awesomeness with these triangles. So if we're talking about an isosceles triangle, the altitude and the perpendicular bisector are the same thing. And if we're talking about an equilateral triangle, oh, and it's also an angle bisector. If we're talking about an equilateral triangle, it's an altitude, it's a perpendicular bisector, it's a median, and it's an angle bisector. An equilateral triangle, those things are all the same thing. So this point right here is the orthocenter, it's the centroid, it's the circumcenter, it's all of those things combined. I'd like for you to pause the video and try to answer the rest of these questions. I do hope that you're pausing and not just ready to copy down these answers. In fact, if you're paying attention right now, please write center in the center of this page. There's all these centers. Here are these answers. We'll talk about this more in class, of course. If you have questions, come see me.